Hello. So today we are going to talk about some interview questions from Google, which were asked on our site and were asked in some of the uh, technical rounds as well as on-site rounds, and has been amalgamated from a couple of resources, such as LeetCode and Coding Ninjas, and also from other sites. So today we are going to talk a few of those problems and how to identify the different approaches to solving those problems. And we begin with a few set of questions that I would like to share. So in this case, I'm sharing my screen to three popular questions which were asked. So the variety of these questions ranges from moderate to easy moderate, somewhere around, I would say 3.5 to 4 out of 5 rankings. And generally, in order to solve these questions, which we'll be doing one by one, is to um, identify the patterns and the algorithms which are involved inside this, right? The second important thing is when you are interviewing for any kind of tech organization, it is better to have the concepts revised regarding, especially for any kind of tech interviews that you are going to do. It doesn't matter what domain it is, the first few rounds is always going to have challenging and innovative questions related to algorithms. So it is always advised to brush up the theories and concepts. And the second important thing is always there can be questions which are cross patterns or cross dimensional. So, for example, you may be asked, cross dimensional questions, such as, one question from trees or graphs, and one from, let's say DP or bit set. That means bit standard bits, right? So one popular question can be, just an easy question to start off the conversation can be, right, find the, or let's say, count the number of set bits in a number, which is a very primitive and an easy kind of a question where, you know, you have a given number, and you have to, let's say, a binary sequence like this, and you have to count the number of set bits inside it. That means number of bits, which is one. So essentially, just a quick hack of this, since I'm already asking this, saying this, so you write something like, you just do take a counter as an, and you do an and one, so that you ensure that, you're counting with respect to one, so that one and one is one, and one and one is zero, one and zero is zero, so that will not be counted. So it will only be counted when one is ANDed with one. And you can do something like, do something like this, where you write shift n by one, then we're moving to the next bit, and you return the count until. So this kind of preliminary easy questions might be started off as a kind of like a conversational stuff, right? There can be some very primitive questions like asking about, given a adjacency, um, ADJ, ADJ matrix, right? Or an ADJ list representation, whatever it is, perform, standard DFS, right? Which can be a very starting boilerplate question, which is easy, moderate, depending upon the level of practice that you have, right? And it's very straightforward, right? So you have a void, DFS function where you take in your arguments, which I'm quoting it over here. You have a start index, let's say, and int start, right? And you write a recursive pattern where you check, you have a visited node. That means you check for visited count, right? How many nodes are actually getting visited, right? So if not visited, the crux of it is if you're not visiting it, then you call in DFS, let's say, source and children, for example, of that particular node, right? Just a brute force DFS, right? Then you can do something like DFS children, You have the adjacency graph before it, right? The children and you have your visited updated. So you can just set the visited of that particular children. Generally do not write source over here, but anyways, you can set the visited as children as one, and then the loop continues, right? So essentially, this is what the DFS is, right? You are checking whether the node is have the children have been visited or not, and then you go towards the children and you go it in a depth-wise manner. So this can be very primitive starting point for your conversations, and then gradually you move to some complicated questions. So let's take the first question without further ado. So the question is very peculiar. It's a very beautiful question taken from one of the Google on-site interviews done by one of my colleagues and also collected from some other sources. So you have been given a binary tree of integers. You are supposed to return the largest subtree sum in the given binary tree, right? So the subtree sum of a node is defined as the sum of all the node values from the subtree rooted at that particular node. So for example, I take a very simple example. So let's say I take one, I do this, you just shift this as over here, right? Two, and if I take this as a very simple example, right? So what is going to be my output? This is my base case, right? You are going to have 6, right? Largest subtree sum in the given binary tree, and it has to be included that node itself. That means the root of that particular subtree also has to be included. So it's essentially 1 plus 2 plus 3, which is 6, and this is the largest if I consider all other subtrees, because you are going to have 2. Let's say if I take this subtree, which is 2, so 2 is essentially nothing but zeros and invalid, right? Null pointer. So it's essentially you are going to have one big tree followed by 2 plus 0 plus 0, which is 2. And you are going to have 3 plus 0 plus 0, which is equal to 3, right? So essentially this, the maximum value that you can get is essentially 6 in this case, right? This is a very straightforward example. Now, the approach one of identifying, when you see this kind of questions, the first thing that you would like to do is it is not possible to always find the optimal solution all the time, right? So in the first case, try to find more examples, right? Examples, how your examples are going to be, okay? Some use cases, some corner cases, right? Try to identify that. The second point is, since this is given as a random tree problem, so it is definitely going to fall into the algorithm of trees, right? So in this case, think whether it can be solved by any kind of tree traversals. So there are multiple of tree traversals, like in the breadth, either in the breadth first search or in the DFS format. So you will have pre, post in order traversals, and you're going to have something like level order traversals. You're going to have reverse post order traversals, right? So essentially, these are nothing but variations of BFS and DFS. So that clears things up. And you are also going to identify, you are going to ask more questions. So if you do not know the problem, ask questions which are related to the problem, right? And this will give a good conversational flow between you and the interviewer, right? Okay, so now since we have this problem, this can be solved in a couple of ways. Since we are the approaching an algorithm, right? That is the main point of this is your code may be incorrect. That is fine, but your thought process should be fine, because the code you can then only fine tune the code after that. So since these are given in the form of subtrees, right? So can we use any kind of traversals for this, right? So since I'm considering a subtree, why not I consider computing the values of my subtrees, that is my left and the right children first, and then the root, which is nothing but pre-order traversal, right? So, a kind of a function would be, right, let's say, if I'm returning an int, or, okay, let's return an int. So int result. So you're going to have, a kind of like a tree index, right? Restart, I'm using the source node, right? And I'm using a counter, which is count, which is, or let's say the result, okay? So what is my algorithm going to be like, right? So it is going to have a pre-ordered traversal. So that means I'm going to check if my if the sum, I'm going to compute the sum of my left and the right subtree, and I'm going to add it to the existing node, right? And I'm going to check whether it is greater. So I have to, what I'm constrained with. So my constraint function is here is that the subtree sum of a node is defined. You are supposed to return the largest subtree sum in that given binary tree, right? So I need a counter which can tell me what is the running maximum value. So I actually need a running counter for maximum value. Okay, that's fine. So this, essentially, this is something I need as a max result, okay, which for computation. And this result is an instantaneous result, which I will be updating. This is both are essentially algorithmic references, and I'm going to update both of them. So we can write something like, we can have an auxiliary data structure, which is a pair of, let's say, int, right? And what will that pair contain? That pair will contain, let's call it as a node and a sum. That means that it will store two things. So what it will contain, it will contain the values, let's say, for this particular 2, it is going to contain the value of that particular node, which is 2, and the value of the 2 plus 0 plus 0, that is the total sum gathered at that particular subtree, rooted at that particular node. So that means 2 plus 0 plus 0, right? Same thing over here. It is going to have 3, and the sum is going to be 3 plus 0 plus 0, right? And I'm just using this for as an auxiliary data structure to the sample space to speed up my process as a brute force mechanism, right? So 1 plus, so this will be 1 followed by 1 plus 2 plus 3. So this has space requirements, right? I'm using an auxiliary data structure, which is a pair. And this space, it grows asymptotically, like as you, so for example, if you have, essentially this will be the number of O of the number of nodes in your particular, okay, multiplied by a constant value k. That k is essentially the sum of your all the values inside of your node, right, of your subtrees. So when you do this, what you can think now is that let's also take this as an input. So let's say where int and say corpus, which holds everything. Okay. So if the left, so let's say if we're root, let's call it as root, not a node. Let's call it as a root. So if root left is there, then what I'm going to do, I'm going to call a recursive function for this, which is updating the root left result max result corpus. Same thing by the root right. Same, I'm going to copy this guy over here. And this is just the pseudocode logic of it. There might be some syntax issues, but you can figure that out, right? So once you have that, you are calling the algorithms on the recursively for the roots first. Now what next? You calculate the sum for this. So so you take the result equal to so this will be result underscore because I'm using a variable for it. So based on underscore, right? Underscore. So the result is going to have, since I'm returning this, let's return it as, let's take variables for this. Okay. I'd recommend not using auto all the time, but you can use it if you are left if you're interested. But and you are also going to have a right subtree. Okay, so essentially you are going to have left subtree, right subtree. Great, beautiful. Now you have this. Now the result for the left subtree dot. So what is your result going to contain? Your result second has the sum. So you're going to have something like second plus right subtree dot second, right? Plus the root t. If I'm considering the data structure of the root, the tree node as something like struct tree. So you're going to have int data. You're going to have tree star left and star right, right? You're going to have like something like this. And so you're going to check if result is greater than. So what are you going to check? Your result is greater than the max result. Okay. And what you're going to do is you are going to update max result as result. And that's essentially it. In other words, you do not need. So probably you don't need the first argument because you have, um, you only need to consider the second argument mainly. You don't have to consider the first argument because the first argument is only for placeholder values. And that is also important. So if the result is max result, and if the interviewer asks you to print out the root node which contains the max sum, then you are going to have something like a tree star max node or max root, whatever you want to call it, is that the corresponding result which is having that. So for example, it is going to be your your current root, right? Because your current root is having the maximum value in this case because we're updating over here. Okay. Yeah, and that's pretty much about it. So if I consider this as a space complexity you have done, time complexity is the time complexity of n, right? Because we're doing a order traversal, or in other words, a log n kind of functionality in this case because you're using a binary tree. So where n is the number of nodes essentially. So now if I consider another algorithm for this, so this is one of the ways you can solve this problem in a very high level. So you can also solve this using DFS algorithm as well. How you can use this? So in this case, you can try something like creating the same thing, but instead of doing pre-order traversal, you can do the DFS kind of a logic in this case. So for example, for every node, there are only two children, right? Check if the two children are visited. If yes, add the values of the children to the root or the parent and continue. If the children are, if they are not visited. If they are visited, then it's no point, right? So we can write something like a int DFS function. Same arguments, I'm just typing it as dot dot for ease of explanation. So here we are going to maintain a kind of like a visited array as well. Visited. So visited is going to be a vector of tree star visited, and it is going to have the number of nodes. That is the number of node count. You can put it as an auxiliary value, right? And inside this, you can say something like um, just for semantic correctness, I'm just typing it over here, right? What are you going to say is that if not visited n, that means where n is the current root. So if I write it as root, and you have the same arguments as before with an additional argument, what you can do is if the children of that particular node is not visited, that means the left and the right child, what you can do is take the root left data plus root right data plus root, and you are going to store that in the current result, right? And that's it, right? And you are going to get the max of max result, comma result, right? And we are going to return the max result. That's it. And that's how it's very straightforward. All right. You don't have, because the DFS will automatically conjure up the next level of iterations, right? So there are some boilerplate codes needed over here, right? Setting up the things and checking whether the root is null or not. But I'm going to just remove that for the sake of explanations. So this is the way. So you can actually solve this in a multiple different ways. Same thing over here. You can also use max of max result, comma result in this case, and you can solve this problem, right? So essentially, this is a DFS problem in other words, right? And every problem which is, every algorithmic problem either can be solved in a BFS or a DFS manner, either in a recursive or an iterative manner. This problem particularly can also be solved using a level or a traversal, which is a breadth first traversal as well. And the way that we are going to use this is for every level, we queue in the corresponding left and the right counterparts, and we can use that as well. Moving on to the next question is that it's a similar kind of a question in the sense that we have the root of a binary tree. It's question number 2, by the way. So question 2. So we have the root of a binary tree, and we return the number of nodes where the value of the nodes is equal to the average of the values in its subtree, right? So the average of n elements is the sum of the elements divided by n and the rounded down to the nearest integer. A subtree of a root is the tree consisting of the root and its all descendants. So it's another similar question like before. Similar question like where we change the cost function. Cost function means the f of x, that is in the previous one, it was addition, right? X plus, x left plus x right. So in this case, we are just going to change it to, change this to something like f of x is equal to x plus x right plus x left and divided by the total number of elements, that is n. That means x plus x, like 3, essentially, right? So this is what it is going to be. So we can take this first part of the question, right? And we can just use this as is and just change this particular part, which is the average, right? We did the total. We now do the average of those particular nodes. Here, the trick is that this value is not going to be 3 all the time. So it can have different values. For example, if I extend this particular question, the 1, 2 example, so let's say 1. So if I extend this, you have 2, right? And after this 3, and after that, I take another, right? And I name the left child of 2 as 4, and the right child of is 5, and I keep 3 as vacant. So for 2, essentially, it is going to have 2, 4, and 5, and for 1, it is going to have 1, 2, 3, 4, 5 together, right? So it is not essentially going to be, it is essentially the entire subtree. So this is very important part of the question like before. So now that we are averaging, we have to keep in mind what is the size of my subtree at each level. So just writing it over here. Caveat here is that you have to keep in mind the subtree size at each depth. Now that's very simple to do because we have a data structure, which is the pair, which can, store the size of the particular element, right? Is essentially going to be n, is essentially going to be the first and the left subtree, first, right? Right subtree first and right, and plus the root, let's say, the root is accounted as 1, so we generally count the root as 1 element. So root plus the left and the right subtree size, and we just divide the average as, result divided by n, right? And the rest of the logic is just the same. So we have two questions asked in two separate sessions or two separate interview patterns having the same pattern of the problem, right? Having the same design of that particular problem. That means it can be solved either by DFS or a p-order traversal. And the solutions are kind of similar because it's just mutating a particular variable that we are holding. So int can be the size of a particular variable. So for example, I'm having int over here, which is the left and the right subtree, holding the size. And instead of the values in this case, I'm storing the values. That is the 1, 2, and 3. What I'm storing over here for this particular question is the size. For example, for 2, the size is going to be 3 and 2 plus 4 plus 5. Okay. For 1, it is going to be the size of this entire subtree, including 1, 2, 3, 4, 5, which is actually 5, followed by 1 plus 2 plus 3 plus 4 plus 5. Okay. So this is the only difference that I'm using. The rest of the part is just the same. I'm just mutating the first part of that pair. The integer is only the difference. Okay, this can also be solved using the DFS part, which the user can, you can play around and find out, right? So these two are the two popular questions which were asked at varying. So these are like moderately good questions, right, for an interview. The next question is related to strings, right? This is related to strings, a very, very beautiful question. And this is probably related to somewhere around moderate to little hard, I would say, moderate to little hard, right? You are giving a string of lowercase characters. Your task is to rearrange or reorder the string in a way that no two adjacent characters are the same. Very beautiful. So if you have to return the rearranged string, if there is no solution, you will say that it's no solution. If you return the if your return value is correct, the program will be incorrect and incorrect. Okay. So let's take an example. What is given? So in the interview, you are given a string AABB, and the possible solutions are ABAB and BABA, which is fine. You can only have interleaving alternate characters. If I take, what is the first principle that we follow now? Is that take more examples. Let's take a more example. Like let's take somewhere around A, A, B, C, C, D. Okay, A, A, B, C, C. Okay, all right. So can we rearrange them in any order? So we can do something like A, then we can do something like, B, we can do something like C, right? And we can again do A, we can do C, and we can do D. This is one valid pattern, right? And there can be other valid patterns as well. So it's not essential that, only this pattern is used. It can also have something like AC, BC, AD. It can also be there, right? So, but there is also one other example. Let's take the edge cases, which is very important. So edge cases are those cases where, it is very interesting and edge cases. So let's take the edge cases. All A's, maybe no solution because they're all A. So there is always going to be consecutive. So can we take another edge case? Like what happens if part of the solution, let's say we take only 3 values, A, B, and C, but they are in different proportions. So let's say I take A, B, C. Will that be valid? So if I take A, I can put in B or C alternately after that, right? In the second element. But then I can again put A, and then I can again put, and let's say if I take the second element as B, then I have to put the third element or the fourth element as C. Okay, and that is done. But what will happen to the rest 1, 2, 3 A's? So they must be consecutive, right? So this breaks the assumption, right? So our assumption was that we can do this with almost any strings, but we found that if all are consecutive, it's not done. So this is also one edge case. So where do we truncate that edge case? Where we guard it? So guarding. Guarding an algorithm, right? Guarding an algorithm against edge cases. This is a very vital and an important thing to always find more examples and do this. We can see that A's count in this example is 1, 2, 3, 4, 5. B's count is 1 and C's count is 1. Great. So total count is, total length of that particular string is 7. Can we let's assume our theorem to be that, for every integer I, every string integer I which has a particular character, the count of I should not exceed or should be less than n by 2. Let's take this assumption that it can be more than average. And why we do this assumption is because averaging something or dividing by 2 something is like gives us a good proportionality that whether my integers are going to be exceeding that particular value or it is going to be less than that particular value, right? It gives a mindset that if I split it into 2, it should not overflow on the other side. 7 by 5, or let's say 5 by 7 is I think it's or let's say if I take here it's 7 by 2, right, which is 3.5, or if I take 3 in this case, right? So if I take 3, this should be my condition that I can balance it safely. If I take 4 or 5, if I take 4, this won't work. If I take 5, this won't work, or any value greater than 3 won't work. And it's quite intuitive, right? So you are going to have only 2 places that different values are going to get filled, the second and the fourth place, and you only are left with 1 place at the end. So 3 is the extrema that you are going to get with this particular value. Okay, and so this is a good valid condition. How to approach the algorithm approach? So this can be thought of as a very kind of beautiful problem in the sense that the way that I'm thinking is I'm counting something, counting the number of occurrences, right? And whenever we count the number of occurrences, we generally involve something called as a hash map, right? So I want to have a hash map which actually counts the number of elements and their corresponding counts, right? So if I write counting, so in COUNT, so what it will do for CS, you can do it in a number of ways. You can take an integer array of 26. You can subtract S of A minus of puts A, and you can increment the counter. Or you can take a hash map as you would normally would, take an unordered map. But in this case, I would not take an unordered map because the algorithm that I'm thinking currently of you doing this is to actually, so how I thought over here is I am prioritizing based upon the maximum occurrence of particular character in that particular string character. So I am prioritizing A over others, right? Because that is the driving factor which can actually make my string compatible, or it will make my string not compatible with the problem statement that I have. Better to use a map so that sorting is in place. Let's take char int mp, right? And mp c plus plus, right? Now you have the count. Let's write it as a white function. I'm not returning anything. So let's return as, so let's think of this as a as the count which holds it, right, in an ascending order. So you are going to have A as 4 in this case. Whatever example you take, and you're going to have B as 1 and C as 1. The next part is something called as how do I design this, right? So since I'm prioritizing on it, can I do a data structure which takes the maximal part? So my workflow, what I'm thinking is going to be, I'm taking in A, which is a count of 4 now. Okay, let's assume, or let's say 3. I'm taking this string, correct string for now as a positive case, right? I have BC as 1. Now, what I'm going to do, let's take a data structure where I first output string is going to be A, right? Then what I'm going to do, C is 1 in the initial step. First, in the output, I'm appending A, right, as the maximal value. Next, what I'm doing, I'm reducing the count of A as 2 because I have already put in A inside the output string. B is kept as 1 and C is kept as 1 as usual, right? Now what I'm doing, I cannot put A again. So I have to either put B or C. So output equal to A comma B. Now A is remaining as 2 and B is remaining as 0 because I have already put B. C is remaining as 1. I can put C or A because B is done. So I only have C or A, right? But if I put C, so let's take this example. If I put C now, what will happen is A is going to be 2, B is going to be 0, C is going to be 0, and my current output is going to be ABC. Okay. But I'm left with two A's now. So essentially, I'm going to be put two A's at the back, but this is not a correct solution. Okay, so this is not a correct solution. Fine. What next? So I have to put A. That means I'm prioritizing on my maximal value. So if I put A, now what will happen? A will become 1. B is out, so I'm not writing B anymore. C is becoming 1. And my string is A, B, A. Now safely, I can put C. And now if I again put A, then again it will be an incorrect combination because A is going to be inverse. So C, I can put the next as C, and finally I can put the end as A. So my final output is going to be A, B, C, A, B, A, C, A. Okay, this is a valid combination. Okay, so now that we have thought about this process, let's try to write it down. Once we have written it down, what do we need? Next is gathering what the information that we need, gathering the info, right? We have done this gathering the info. We have a dry run of the algorithm. Now what data structures I need? So since it is something based on a maximal ordering, I would need a kind of a data structure which pushes and pops based upon maximal values. And one of the most popular, and I don't need any kind of ordering between them, right? Only I'm concerned about the maximal values, right? So I can use something like a priority queue, right? And let's take a priority queue. I'm writing it as PQ for abbreviated short. Inside this, I'm going to take a pair of ints, char and ints, for example. So it is exactly going to do what we have just seen. So it is exactly going to take what it is going to take for every step. It is going to take A and 2, let's say C and 1, which is the maximal element at that particular point of time, right? So we insert initially for the first part, we insert two elements, which is, let's say, an absurd element like let's take an array character hash followed by a count 0 or -1, whatever it is, just for placeholder values. Now, while not PQ empty, what I'm going to do is, let's try to write something, right? While my priority queue is not empty, I'm going to iterate, and this is going to be the maximum element of my queue of this entire thing is going to be the root. So this is going to be a maxi kind of maxi, right? Maximum element is at the root. You extract the top, which is, let's say, an auto top. Okay. Now, once you have this top, what are the two elements inside that top? You are going to have the character and you are going to have the integer, right? Integer, which is the count of that. So you are going to do top dot, let's say, you know, second, right? second minus one, because you're reducing the count of that particular element. But what are you going to do with the first one? So in this case, you have to keep in mind what the previous counter was. For example, we always kept in mind, for example, A is 1 and C is 1, right? In this case, controversial case, if I put a now, right, I have to keep in mind what I had kept in the previous step. So I need something which stores that previous step. So this top dot front, sorry, top dot first is going to have my previous. This is going to be my previous. Okay. If the previous count is still greater than 0, that means if my previous has not extinguished yet, right? What I'm going to do, I'm going to put PQ dot push, right? Previous, comma, and I'm going to take the reduced counter. So this I'm, taking a value, let's say auto val equal to top dot second minus one, right? Right. So I'm pushing it as val in this case. Now, why I'm doing this? Why I'm doing this? Why? The reason is that, let's say A is equal to 2 after this stage, right? A is 2 after this stage. A is 2 and B0 C is 1, right? So A is reduced to 2 after 3, from 3. Now, in order to ensure that I do not get this misconfiguration, I have to keep in mind that my previous was B. And then I can select either C or A. But I should be selecting A because my A's count is 2 now from 3. So that is why it is needed. What next? The next is the most important step, is because prev is now going to be your top. Top is your essentially your current, whatever you want to call it. So you are saying that if you allocate C over here, right, which is the incorrect by combination, then this C will become your previous, right? And when you go to C and it will pop the C, the C's count will become 0 and you're only left with A. Now the previous and so your heap will become empty, right? And you will not be able to perform any more steps, but you also have two A's left. So that will give you an invalid combination. So this is needed to ensure that your A and your C are essentially, you put the A before you put the C. Okay, so that is why you do something like previous equal to top, where you're setting the previous as the current element, right, after this pushing back. And what you can do to check, and the last part is that if the result dot size equals your you have to also put your so yeah, I forgot to mention that you also need your string output, right? So string OP, right here, OP plus your essentially top dot first, right? Top dot first is your OP, top dot first is your OP, and your top becomes your previous. Okay. And so OP is, and we're going to return the OP. Okay. If result dot size, which is essentially the OP, that is the output dot size. So if output dot size is essentially your input string dot whatever you want to call it, s dot size, then it's a match. Just see out correct whatever it is, right? And rest you can do incorrect whatever it is. So this is one algorithm which you can design, and you can try it on this, and you will probably get a correct solution for this particular case. So we have used something like a maxi for this beautiful problem. We can also use a general sorting algorithm for this as well. So we already sorted all the elements in an order inside my count. Okay. So next, recreating this can be a decreasing order of that particular hash map, right? But you have to keep in mind this particular condition, that if previous is greater than 0, that means you append it back to the maxi, which I did, reducing the count. And you also have to keep in mind that what your current element is and what your previous element was, the count of that. Okay. So this can also be done with a simple sorting as well, right? And Referring, so the algorithm will remain the same, that take the sorted array of characters and integers that you have the pair probably, and check if the previous occurrence of the element, right? If it is greater than 0, then you push it back to the array and you recount the, else if it is not 0, then push the current element as the push the current element as the previous element. Okay, and you're done. So this can also be solved in a sorting approach for simplistic use cases. But this is how the problem is. It's a very kind of a tricky problem. And this is a kind of like a problem which gives you have to think about. So if I estimate this problem is going to take somewhere around 40 minutes of good time, right, to do a good analysis and write a clean code, right? Because this is containing a lot of syntax issues, but an algorithmic, some kind of issues might be because I've not written the full code. But if you're writing the full code, it can be taking somewhere around 40 minutes, an estimate. So these were the 3 questions that I extracted as my first, how to solve or how to go about approaching a particular problem. Think that these data structures are the biggest tools that can help you to actually solve a particular problem, right? And it is so you can try. So I went to the optimal or the suboptimal solutions in the first case, but always try to see brute force first. So for example, is a brute force for this third question, how you're going to, what is going to be the brute force solution, right? So brute force is going to be iterating one by one and checking each element, right? And checking whether the occurrence is greater or not, like how I did this pseudocoding or this dry run. For these particular questions, the brute force was the standard algorithm, so it was pretty straightforward in this case, right? So that's it for this video, and I will again return with more interesting questions from other organizations and other collected from different sources and interviews which I take or which I hear from others. And yeah, please do like and subscribe. Thank you.